Hi, my name is Erin Good, and today I'm going to talk to you about the creation and commissioning of new experimental systems, in particular the split-pole spectrograph set up at Florida State University. So to start us off, we'll have to go back to the event that started it all in 2011, which was sadly the shutdown of the tandem accelerator at Yale's Wright Nuclear Structure Laboratory. My grad school advisor, Catherine Deibel, who was a former Yale grad student and current LSU professor at the time, heard this news and was like, hey, I wonder what they're going to do with the split-pole spectrograph. So she went to her fellow collaborator, Ingo Wiedenhöver at Florida State University, who helped run the John D. Fox Accelerator Lab at Florida State, and asked if he'd be willing to take on a spectrograph if she could get her hands on it. And he said, sure. So they asked the people at Yale if they could have the old equipment from the lab, and they said yes. So at this point, you're probably like, what's a spectrograph? So let's just walk you through the experimental setup that they had at Yale and that they were hoping to set a similar type of setup up at Florida State. So the split-pole spectrograph, or SPS as I like to call it, is this large portion of the setup here. It's a 34-ton magnet that can momentum analyze particles. So how does this whole setup work? Well, first you shoot a beam at a target here in the target chamber. A reaction occurs and you'll have an excited state of a nucleus populated in your target and some reaction product that's lighter that continues on through the magnet. And these products are momentum analyzed in the magnet and spread out according to momentum along the focal plane, which is where we have a focal plane detector set up. This is a gas-filled ionization chamber that measures residual energy, energy loss, and the position of those particles. And that position tells you what state was populated in the excited nucleus. At the same time, we have ILSA in the target chamber, which is a charged particle detector that detects any particle decays from that excited nucleus. So all in all, we are capable of measuring the energy of excited states populated in nuclei, angular momentum transfers, which we can measure by rotating this whole spectrograph around the target chamber. And we also get angular momentum information from the segmentation of the charged particle detector. And lastly, we can measure particle decay branching ratios. So a excited state of a nucleus will decay via a charged particle or a different charged particle or a gamma ray any number of times. So if you have a excited state and it decays via alpha particle 50% of the time, the alpha particle branching ratio is 50%. So this is how the setup was used. And at Yale, it was used in a robust scientific program that used a lot of stable beams to measure a variety of nuclear physics quantities. So a lot of times in nuclear physics, we like to measure a cross section, but if the beam isn't able to be created, or for example, it's like too radioactive to be a target, that's where indirect measurements are really great. And so you can use these nuclear properties that are measured indirectly to obtain things that relate to things like the cross section. So here on this slide, for astrophysics, we like to use a type of cross section multiplied by Avogadro's number and some temperature information called the astrophysical reaction rate. So here, this is the astrophysical reaction rate equation, which you can calculate, but you need some measured quantities. And here, the highlighted quantities, the resonance energy, angular momentum transfers, and charged particle branching ratios, those are all quantities we can measure with the split-pole spectrograph. So when you put in known quantities as well, you can calculate that reaction rate for when you can't measure what you want to directly. So it's a really great program that we can do with the SPS. So that's why my grad school advisor, Catherine, didn't want this magnet to just go off to the dump. So the plan was to take this magnet to Florida State and to upgrade the existing detectors and electronics. So firstly, we were going to redesign the silicon array, ILSA, for high geometric efficiency and rename it SABRE, the silicon array for branching ratio experiments. The other goal we had was to incorporate new digital electronics to achieve lower thresholds in SABRE. So I'll talk about those things in the whole process of what all had to happen for this magnet to get to Florida State and get set up and run and get funded. So after that initial question of, can I have this magnet, the whole process started in 2013 when the split pole was loaded out of the Wright Nuclear Structure Laboratory here and loaded onto an 18-wheeler to go to Florida State. So you can see it's a pretty big magnet. It's 34 tons, and this is a human to compare. So that was driven down to Florida State, and then application for funding began. So both Catherine and Ingo had to apply for an NSF Major Research Instrumentation Grant, first going through their universities and then actually submitting to the National Science Foundation. So that was started in 2013 and submitted in early 2014, and then by fall of 2014, they got confirmation that the grant was awarded. So now we can pay for things. So this covered the installation of the magnet at Florida State, all of the support systems like the power supply, gas handling systems for the magnet, as well as the SABRE detectors and electronics. And here I just have a snapshot of the proposed project schedule as it was planned in 2014. So here you can see we're trying to do first experiments by fall of 2016 and spring of 2017. So will that happen? You'll find out by the end of the talk. In summer 2015 was when I first joined this project, and I started by designing the new SABRE array during my first summer at grad school. So to do this, I was simulating various designs of detector arrays with different types of detectors that are available on the market for maximum geometric efficiency. And I ended up settling on a design of 5 triple M detectors by Micron Semiconductor. And this design actually doubles the geometric efficiency over the old array. So that was pretty cool. And then September of that year, we placed an order with Micron Semiconductor to get these detectors because they had like a 9-month lead time. So we wanted to get this done so that we wouldn't be waiting on detectors. The next year, at 2016, we started repairing the focal plane and testing it at LSU. So this involved polishing the scratched cathode plate, repairing some field shaping wires, and I supervised Pham, who was an undergraduate student at the time, while he was testing the focal plane detector to see if it still worked. So he was testing a variety of gas pressures for the detector, biases for the different electronic components inside, and he was also making a sliding source holder so that we could move an alpha source to see if the position would show up on the detector, which it did. At Florida State during that year, they were busy getting a fancy new floor and concrete pedestal. So they hired outside contractors to drill test piles to see if the floor would actually be able to support the 34-ton magnet and pedestal. And it turns out after they drew a test pile, it would do that. So they drew up some final engineering plans and had to submit them. And during that summer, they drilled the rest of the support piles. I think there's at least 40 in the floor, if not more, before they laid this concrete pedestal. And then this had to sit for about 6 months to make sure it was like solid before the magnet was installed. So back to LSU during that time, I was working on creating the SABRE mount. I created CAD drawings for all the parts. We had to submit the CAD drawings to the LSU machine shop. And then I was working closely with them once the parts were fabricated to make sure everything fit together as we expected, and working on getting everything lined up just right. Because as you can see, there's not a lot of room for tolerance here. So 2016 was a busy year at both places. But in January 2017, we first started seeing things come together when the split pole spectrograph was finally installed on that concrete pedestal at Florida State. So it was installed, but there were still all of the support systems that had to be placed. So that happened during the next 2 years. The power supply was connected to the magnet, which involves a big box and a water cooling system, and these huge cables that you can see that have to come over. Additionally, they installed this target chamber and a crane to lift the lid because it's a pretty big lid and you can't lift it by yourself without damaging anything that's mounted to it, like SABRE, the detector system. They also got installed and operating the gas handling system for both the magnet and the target chamber. And then finally, they got the beam line installed and they aligned that with the target chamber and made sure everything was all lined up and ready to go. So here you can see the beam line, and here's a quadrupole focusing magnet. During those 2 years at LSU, we were still busy, but doing other things. So we were building preamplifier boxes, ordering electronics modules, and testing digitizers. So one of the first things we did was I designed custom printed circuit board feed-throughs. As you can see here in black, that's a design. So those were made to fit the existing target chamber lid for SABRE and to get the signals out. We also modified the preamplifier boxes at LSU and built 3 of them for SABRE. And during that time, we tested a variety of different digitizer modules, which is the digital electronics component of this. These are relatively new, and we settled on Cayenne 1725 digitizers. And we had to order about 8 of them because we had 120 channels coming out of SABRE. And so we ordered our digitizers. We ordered these MDU modules, which apply gain and convert ribbon cables to LEMOS for the channels. We also ordered a DAC computer, and we ordered so much ribbon cable to cable everything. So there was a lot going on our end too, just not quite as exciting as seeing that magnet installed. So that brings us to February of 2018, which was when the focal plane detector was brought over from LSU to Florida State and first installed and tested. There was no beam line at this time, as that was still going on, but you didn't need a beam line to test the focal plane detector. All we needed was the gas handling system and the power supply. So here you can see me and our postdoc at the time, John Lighthall, installing the focal plane detector in the camera box. And then we use a crane to put the back door on here. So this involved us hooking up the gas handling system and installing electronics. And so when this was all zipped up and pumped down so that there was no gas, we installed a thorium source in the target chamber, turned on the magnet to about 5.8 kilogauss, and tried to see if the focal plane detector could see those alpha particles from the thorium source, and it did. So that was super exciting for us after working so hard to get this thing tested and installed. Later that summer, it was even more exciting when we first commissioned the focal plane detector and the split pole spectrograph with an actual beam on target. So officially, commissioning is the process of making sure that your detector system works the way you expect it to. So we have to take a well-known reaction or quantity and measure that to see if we're seeing what we expect. So here we took the 12 carbon DP reaction to populate well-known states in carbon-13. So we used a 16 MeV deuteron beam on a 200 microgram per centimeter squared carbon-12 target. And as you can see here, we see the ground state and the first 3 excited states of carbon-13. We also see the ground state and first excited state of oxygen-17. And that may worry you, but it shouldn't, because that's the oxygen-16 DP reaction we're seeing. And we see oxygen because water is everywhere. So that's just some water contamination in our target. So we got some bonus peaks. So everything here was working as it should, and we were able to achieve similar resolution to when this detector was installed at Yale. So it was considered a success. So after that, the SABRE team pushed onward, and From fall 2018 to summer 2019, we worked on installing SABRE in the target chamber and doing the first alpha source tests. So we took almost a trip a month to Florida State during this time. So many trips to get this done. We had to install SABRE, make sure it fit in the target chamber, because even though it was designed to, you never know until you get there. We had to align it and make sure it was lined up in the center of the beam line. We made a whole bunch of cables for the electronics and inside the target chamber with the feed-throughs. And a lot of work during this time went into setting up the planned data acquisition system, NSDL DAC, finding out that wasn't going to fulfill our needs, and transitioning to a new data acquisition system called Compass. And Sudarsan, a fellow grad student at LSU at the time, did a fantastic job on all of this. So part of that transfer of data acquisition systems also had us transfer the focal plane detector to those digitizer electronics. And honestly, that was really great. We got even better signals than we saw with the conventional electronics. So it was a little perk surprise that we ran into. So here you can see at the end of summer 2019, us testing SABRE with an alpha source in the target chamber, that same thorium source, and seeing those custom peaks. Which brings us to fall 2019, when we did the commissioning run of SABRE with the split-pole spectrograph. So as this was like the main focus of my thesis, I was really excited for this. So we were looking at known 100% alpha particle branching ratios of states in 16 oxygen via the 19 fluorine P alpha reaction. And so this is a little complicated, so I just want to walk you through it quickly. This is a proton beam, and that impinges on a 19 fluorine target. The reaction occurs and leaves an excited state of 16 oxygen and an alpha particle reaction product that travels through the spectrograph and is momentum analyzed to tell us what state of oxygen 16 was populated. Then that excited state of oxygen 16, which remains in the target, de-excites via a charged particle emission by this green alpha here into SABRE. And so we're able to measure alpha particles detected in SABRE and how many times that occurs in coincidence with the alpha particles that say we populated a state in 16 oxygen. So we're looking for a ratio to see every time the 16 oxygen is populated, does it decay via alpha? And that is what we expect here. So to briefly walk you through this commissioning experiment analysis, just so there's a smidge of science in this talk, the first thing we do is we want to plot the focal plane position on the x-axis versus the energy loss in the focal plane on the y-axis to identify these alpha particles in the P alpha reaction. That tells us we're looking at states in 16 oxygen. We draw a gate around those particles, those alpha particles, and project it down onto the focal plane position axis. And then we see the states we're interested in, which are labeled here, the ones with 100% branching ratios. So we count the number of counts in those peaks. Then we make a similar plot of the focal plane position versus SABRE energy and gate along this characteristic line. And that's the alpha particles we see decaying from 16 oxygen. And the states, when we project this cut down onto the focal plane position axis, we once again see those states, but only when an alpha particle decays. So we count the number of counts in these peaks again. And remember I said the branching ratio is a ratio. So we take the SABRE counts over the total focal plane counts to get our branching ratio. So here we compare these to a simulation of geometric efficiency, because we expect a 100% branching ratio, but the SABRE detector doesn't actually cover 100% around the target. So if our measured branching ratio matches our calculated geometric efficiency, that's indicative of a 100% geometric efficiency. So all of the states of interest agree with our measurements within errors, so we were able to say SABRE works. So following that commissioning experiment and in through 2020, we were analyzing the commissioning data and performing the first experimental runs. So we made further improvements to the digital data acquisition scheme during this time. We did further physical shielding and biasing for SABRE to deter electrons and heavy particle backscatter. The event building pipeline was continuously improved, primarily through the work of Gordon McCann at Florida State, who did a fantastic job making really nicely packaged software for that. And then we have a variety of first experiments. So we were able to study branching ratios for the aluminum 26p gamma reaction in classical novae. We were able to study highly excited states in 9 boron via the 10 boron helium-3 alpha reaction. And these are important for lithium-7 abundances and Big Bang nucleosynthesis. On the nuclear structure side, we were able to look at low-lying resonances in 9 boron using SABRE as a coincidence array. And we were able to look at interference effects between 2 resonant states in 13 nitrogen via the carbon-12 helium-3d reaction. So there was a lot of really interesting science going on, even with the pandemic. And finally, in 2021, the Nuclear Instruments and Methods article announcing basically that SABRE and the SE-SPS are here and ready for you to do your science was published. And we finally finalized the split pole name and came up with the Super Enge Split-Pole Spectrograph. It all grew on us eventually. So just to wrap up the talk, I just want to bring you back to this proposed project schedule from 2014 and show you that even though we planned to do our first experiments in fall 2016 and spring 2017, things just never come out as quickly as you plan for. There's always something to hold you up. But we finally got there. SABRE and the Super Enge Split-Pole Spectrograph are now running regularly for a whole bunch of experiments in nuclear structure and astrophysics applications. And we were able to achieve our design goals of lower thresholds and higher rates with this new setup. So I just want to thank everyone at LSU and FSU that worked so hard on this project, getting it off the ground, our funders, and the Krell Institute for running this fellowship and providing just a fabulous experience during my time in grad school, especially when I was so stressed out about this commissioning. So thank you all so much.